Hi everybody. So today I want to start a new chapter on Chapter 9, which covers static equilibrium, elasticity, and fracture. So first let's talk about the conditions for equilibrium. So equilibrium basically just means the object isn't accelerating at all. So an object with forces acting on it that's not moving is said to be in equilibrium. And in that case you have forces that are equal but opposite in direction in all directions. Now, the first condition for equilibrium is that the forces along each coordinate axis add to zero. So this should remind you of those problems that we did in a previous chapter where we do our free body diagram and then we sum the forces in each of the directions independently. Except with equilibrium conditions, it's even easier than it was before because there's no chance that this object is going to be accelerating in any direction. So you just set the sum of the forces in each direction equal to zero and you can solve, and it's actually a somewhat simpler problem. But here's where things get a little complicated. We've also got rotation to think about. So in this little example with the ruler right here, the forces are equal and opposite. So that means that the ruler won't translate along the table, but it will rotate because there is going to be a net torque on that particular ruler. So in order to truly have an object in equilibrium, you have to have no net torque around any axis, and you have to choose the axis, any axis, right? It has to be any axis with no net torque. We've already learned all the physics that we need to do these problems. We learned about summing the forces and setting them equal to zero, and we learned about summing the torques up. Okay, we've solved problems that way. But now we just kind of have to combine that knowledge. So to solve statics problems, you use a lot of the same techniques that you used in previous chapters with torque and with the free body diagrams. So you just choose one object, you draw your free body diagram showing all your forces and where they act. You choose your coordinate system, resolve those forces into components, and then write the equilibrium equations for the forces. And also you need to consider the torques. So you choose an axis perpendicular to the plane of those forces, and then write the torque equilibrium equation with respect to that axis. And if you're clever about where you choose it, then you make it a lot simpler. And that's where the real gift comes in, I guess. But then once you've written down all the equations, all you have to do is solve. So probably the best way to show you what I mean is just to do a couple of example problems. Because like I said, you've already learned all the physics. You just need to learn how to apply that physics to this set of problems with equilibrium conditions. So here's an example problem from your book. And this one says, how close to the edge of this 20-kilogram table can a 66-kilogram person sit without tipping it over? Okay? So between the legs of the table, you've got 1.2 meters. It's a nice symmetric table. If I were to fold it in half along the middle, it would look exactly the same. The table is 0.8 meters high, and there's 0.5 meters from one of the legs to the very edge of the table. All right, well, let's look at how to do this problem. This table is nice and symmetric. So what that means is that we know that our center of mass for the table would act at the center of the table. So on the free body diagram here, I've drawn little mg straight down at the center of the table. Now remember, it was 1.2 meters between the table's legs, so from the center of the table to the right leg, that's 0.6 meters. Okay. Now, that person sits on either edge. It doesn't matter because since it's a symmetric table, they could sit in on the right side or the left side, and in order to get it not to flip, it would have to be the same distance from the edge of the table, if you understand me. So let's call the mass of the person big M in our equations, okay? And they're going to sit on the right side of the table at some distance x away from that table leg, okay? Now, what's going to happen is we're going to assume that the table is on the very verge of tipping, so that the person sits as far as possible from that edge and it just starts to tip, but not quite. Now, if the table were to tip and they were sitting on the right side, then what would happen is that left leg would come up off the floor. And if that was the case, then the normal force of that left leg pressing on the floor would go to zero. So we're going to have a threshold value, and we're going to say that there is no normal force on that left leg. Of course, there'll be lots of normal force on the right leg because basically the right leg will be the only thing holding that table up. Okay? So the normal force on the right leg is a big number, but the normal force on the left leg is 0 because it's just getting ready to tip. Okay? So the person I've drawn with a big mg for the free body diagram for that person acting at some distance x from the edge, and then you have a normal force, a large normal force on the right leg, but nothing on the left leg. And so that's the free body diagram for my table. Now I'm going to use this free body diagram information to solve my problem. So basically we're talking about a tipping, so that's a rotation. So we're going to do the sum of the torques for this to solve the rotation problem. So we're going to calculate the torques about that right leg of the table because that would be the rotation axis, right? It's going to rotate about that leg, about that point where it's sitting on the floor, okay? We're going to call counterclockwise torques positive, and we're going to call clockwise torques negative. Now, the torque from the mass of the table, that would be counterclockwise. That would want to rotate the table this way, okay? So that would make the table stay down. Whereas the person sitting on the edge of the table, that's a clockwise torque. It has a tendency to tip the table up, okay? And so that will be a negative torque. Now remember that the value of the torque is equal to the distance from the axis of rotation to the point of application of the force, right? And then times the magnitude of the force and times the sine of the angle in between R and F, okay? So in this case, you have 0.6 meters from the rotation axis to that little mg, okay? And then there's a 90-degree angle between mg and R, right? Okay, so that gives me a torque for the positive torque for the mass of the table is little mg times 0.6 meters, and then the sine is the sine of 90 degrees, which is 1. Now, the mass of the person, that's going to be a negative torque, so it's minus big M, that's the mass of the person, times g, and then times x is the distance from the axis of rotation to the big person. Okay? Now, the normal force, it doesn't cause any torque because it acts right at the axis of rotation, so the lever arm is 0 in that case. Okay? So the normal force from the point of application of the force there at the table, that doesn't play into the torque at all. So you just have little mg times 0.6 minus big mg times x is equal to 0. And now we can solve, okay? We know the mass of the table and we know the mass of the person, and so we solve and we get x is equal to 0.6 times little m over big M, which is 0.6 times 20 kilograms, the mass of the table, divided by the mass of the person, 66 kilograms, and that gives us x is 0.182 meters. Now, it asks for the distance from the edge of the table, and x was the distance from the leg, and so you need to do 0.5 meters minus 0.182 meters to get the distance from the edge of the table, and that gives you 0.32 meters. Now, there's also lots of statics problems that have cables and cords. All right, so it's important to remember that for cables and cords, it supports the force along the length. Remember that the tension, which is what you'd have if you had a cable or a cord, a tension force acts along the cable. Okay, so let's do an example problem with a cable or a cord. Here we have a traffic light hanging from a pole as shown in this figure here. And it's a uniform aluminum pole that's 7.5 meters long from A to B. And it has a mass of 12 kilograms. And then it supports a traffic light, which has a mass of 21.5 kilograms. And what they want is the tension in this horizontal massless cable that runs from C to D here in the figure. Okay? So yet again, this is one of those things where you're going to have to calculate a torque. All right? So the pole is in equilibrium, and so the net torque on it has to be 0. Now here's my free body diagram. Okay? I have the tension T that acts along that cable from C to D, and it's pulling the cord is pulling that pole to the left. All right. Now, there's also a force from the mass of the aluminum pole itself, and that's little mg here in the figure, and it acts at the center of that pole. Now, the traffic light also causes gravity pull down, and that is big mg, and it acts at the end of the pole. Okay? Now, all three of those forces, the tension, the little mg, and big mg, those all will cause a torque. Now, the axis of rotation is right here at point A. That's where everything is going to rotate. Okay? Now, remember, a torque is equal to R, the lever arm, times F, times the sine of the angle in between R and F. Okay? Now, yet again, I'm going to take counterclockwise torques as positive and clockwise torques as negative. So if you look in this figure, the tension would cause a counterclockwise torque, and the gravity acting from the pole and from the traffic light would cause a clockwise torque. So those two will be negative and the tension will be positive. Now remember, it's RF sine of phi, the angle. So here, for the tension will be symbolized by capital T, and then from the rotation axis, it acts a distance L. Okay, so L is the lever arm. And then there's the sine of 37 degrees in between the tension and that F. So the sine of 37 is the angle. So that's your positive torque. Now, the gravity from the stoplight will be from big mg, and then it's a distance big L from the axis of rotation. Now, the sine of the angle in between there is sine of 53 degrees, okay? Because you have this pole that keeps extending up. If this angle over here is 37 degrees, then it's going to be 53 degrees between the other angle, for the other angle hanging down, because it would be a 90-degree angle, and 90 minus 37 is 53, a 90-degree angle in between the horizontal and the vertical. Okay, so it's sine of 53. And then similarly, the gravity from the pole acts in the middle of the pole, so there the lever arm is L over 2, and it's minus little mg L over 2, and yet again, sine of 53 degrees. Now those torques all sum to 0. Okay, so you can solve algebraically for what the tension would be, and you get mgl sine of 53 plus little mg L over 2 sine of 53 divided by L over sine of 37. And when you plug in for the value of L, which is 7.5 meters, little m, which is 12 kilograms, and big M, which is 21.5 kilograms, then you get 425 newtons for that tension. Now, I know a lot of you are majoring in biological applications, you're interested in med school, so it might be of interest to you to figure out how this applies to our bodies, to muscles, joints, things like this. You can use the exact same principles to understand forces within a body. For example, the amount of force that your muscle has to exert to hold balls or weights at some angle with respect to the joint. So let me do an example problem for that one. Here, this is another one from your book. The Achilles tendon is attached to the rear of the foot right here, okay? And when a person stands on their tiptoes, just barely elevates themselves off the floor on the ball of your foot, they want you to estimate the tension in the Achilles tendon, which pulls upward, and then the downward force exerted by that lower leg bone, that big bone there on the foot. What you're to assume is that the person has a mass of 72 kilograms, and then the distance here between the ball of the foot and the leg bone, big D, all right, is twice as long as the distance in between the leg bone and the Achilles tendon, little d, all right? Now, what's going to happen is, here's my free body diagram. I've totally simplified it. There's no muscles or anything now, and I've just got a little rectangle to symbolize the foot, okay? And you can simplify things like this with the physics problems, and it works just fine. Now what you're going to have is you're going to have a normal force between the foot and the floor acting at the ball of the foot. And that normal force will be the person's weight, right? Because all of the person's weight is going to be pushing down on that point, and the floor pushes back equal and opposite. Okay, now we're going to calculate torques about a point on the floor that's directly below that leg bone, which is right here at F sub B. Okay? Now, this is an equilibrium. You're assuming that they're holding still, so the sum of the torques will be 0. And yet again, we're going to take counterclockwise torques to be positive, and then the net force in the y direction also has to be 0, and we'll end up using that to find the force on that bone, F sub B. But first, let's do the torques. So you have the sum of the torques, and you set that equal to 0. Now, the two things that are going to cause torques, remember, the force of that bone, F sub B, that acts at the axis, so that causes no torque because the lever arm is 0. So you just have the force of the Achilles tendon and then the normal force that are causing torques. Okay? Now, the normal force, that's going to cause a counterclockwise positive torque, and then the tendon is going to cause a clockwise negative torque. Okay? So you have your normal force, and then the lever arm there is 2d, or 2 little d, or big D, okay? So F sub n times 2 little d, that's our positive torque, minus the force of the Achilles tendon, because that's our negative torque, times little d. And you sum that and set it equal to 0. Okay? Now you can solve for what the normal, or the force of the Achilles tendon is. You know the normal force is the weight. Okay? And so what you end up with is, if you solve this little equation, you get FAD is equal to FN times 2D. The D's cancel out because they appear on both sides of the equation in every term. And you end up with the force of the Achilles tendon is 2 times your normal force. Well, 2 times your normal force is 2 times N times G. The mass of the person is 72 kilograms, and of course G is 9.8 meters per second squared. And so that gives you a force that the Achilles tendon has to exert of 1.4 times 10 to the 3 newtons. Okay? Now that you have the force on the Achilles tendon, you know that the net force in that y direction has to sum to 0 because the person's not hopping up and down or anything. They're holding still. And so you have some upward forces, the force of the Achilles tendon and the normal force. Those are going to be positive because they're in the positive y direction. And then B, the force on point B, that's in the negative y direction, so that's a minus. So you have the sum of the forces in y is 0, which is equal to Fn plus Fa minus Fb. And then you can solve for Fb because you know now the normal force, which is 2 mg, and the force in the Achilles tendon there. And so you can solve. I'm sorry, the normal force is just mg, and the force in the Achilles tendon, which is 2 mg. So 2 mg plus mg is 3 mg. I'm plugging in 72 kilograms for m and 9.8 meters per second squared for g. You get 2.1 times 10 to the 3 newtons. All right. So to finish off this lecture, I'd like to just say a few words about stability and balance. Now, if the forces on an object are such that they tend to return it to the equilibrium position, then that's a stable equilibrium. And we studied some things like pendula and springs, and those forces have a tendency to restore it to that middle ground equilibrium position. So those are stable equilibrium kind of points. If, though, your forces tend to move it away from equilibrium, like trying to balance something very carefully, then it's unstable equilibrium. So if you can manage, in other words, to balance a pencil or a pen on its end, it's very difficult. But if you can manage to do it, then even just a small little breath of air would blow it over. And so that's an unstable equilibrium point. If an object is in stable equilibrium, it could become unstable if it's tipped, and I think anybody that's ever moved furniture can tell you this, okay? And that's because the center of mass, or the center of gravity, gets outside of the pivot point. So as long as the center of mass or the center of gravity is over the pivot point, you're good, but if the center of mass or the center of gravity gets away from the pivot point, it'll tip over, all right? And that's bad. Of course, once it lands, it'll be stable again, but then it's already crushed your toe. Now, people that carry heavy loads have learned over time, while they learn to walk as kids, to automatically adjust their posture so that their center of mass is over their feet. But for you people in the medical world, of course, that can lead to injury if you have to contort your body too much or cause stresses. Okay, so that's everything that I think I wanted to say so far, and I'll see you in class.